previous lecture, we started discussing magnetism. And we saw that there are two different mechanisms by which electrons gain magnetism. One was basically based on the Zeeman effect. We saw that if we apply a magnetic field due to the Zeeman effect and the Pauli principle, we can get a magnetic response. The response was paramagnetic, and we have seen all details. We were in the middle of trying to figure out what is the orbital response. Now, for the orbital response, we have to take into account the fact that the electrons in the system are described by a Schrödinger equation, and solve the Schrödinger equation in the presence of a magnetic field, a thing that you haven't done in quantum mechanics. So, we wrote... You did?
I think we did. With
Right.
what? We solved Schrödinger equation with the presence of magnetic field? Electric field?
We started.
We started, we didn't finish, we were halfway through.
No, in the quantum mechanics.
We are talking about it's a quantum mechanics course, not
I
this.
think we did.
Yeah, we
Some of
calculate
us,
the
some
energy
of us.
difference for the Zeeman effects.
No, it's not Zeeman effect.
So, no.
No. Okay, no.
So either you were in two different courses, or each one of you took something else out of the course. Or we have a clear case of Rashomon. Okay. Anyways, I'm not taking into account the fact that you may or may have not solved the Schrödinger equation. We are in the middle of solving it. So, where were we? We started from the Hamiltonian of free electrons, meaning that we still do not consider what happens due to the presence of a lattice in this game. We'll start considering lattices in the second part of this lecture. But the fact that we have a magnetic field changes our Hamiltonian. As in classical analytical mechanics, we added the influence of the magnetic field as a vector potential. We chose a specific gauge. Pointing writing Y. We saw that it actually describes the system, and after guessing a solution, Y. We inserted it into the Hamiltonian, and we ended up with the following equation. And we ended with the observation that up to constants, this is the equation of an harmonic oscillator in x direction. Okay, so we'll go and just rewrite it in an easier form so we can just quote the solution of an harmonic oscillator. But as physicists, something should bother us a bit. And what is it?
With the quantum result, what should bother us?
I'm looking at this equation, remembering my initial problem.
It's just a harmonic oscillator along the x-coordinate.
Okay, so rephrase it in
in our classical model, which the classical being the expected values, we should get circular orbits, meaning it should be a harmonic oscillator by the x and y coordinate.
I'll treat you like ChatGPT. Simplify your answer.
It should be according to the r radian, to x squared plus y squared.
So let me rephrase your answer, which is correct, but it's not the form that physicists usually will express themselves in this problem. In the initial problem, there was symmetry between x and y. Why? Because the only thing that breaks symmetry here is a magnetic field in the z direction. Okay, so I can understand why z behaves differently than x and y. Actually, it makes a lot of sense, because in classical physics, if we have a magnetic field in the z direction, the result is an orbiting in xy plane and a free motion in the z direction. Therefore, this guess is almost trivial. Of course, what else could it be? But why is the symmetry broken in the xy between x and y? And the answer is because we decided to break it. We did it. Now, there is a logic behind why we chose to break it in this form, but I'll discuss it once we see the full solution.
You could also, to retain the symmetry, you would do in AX, you would put B 1/2 BC minus.
Then it will be symmetric and it will become very difficult to solve the problem. And well, that's one explanation why I did it, but the other explanation is actually it makes a lot of sense to break it in this way. Why? Because at the end of the day, I would like to use the solution here to describe Hall conductance. And what is special in Hall conductance? We have an infinite behavior in one direction and boundaries at the second direction. Therefore, also the physics is broken. That is a deep reason beyond mathematical niceties why I did break the gauge symmetry in order to be able to accommodate the boundaries more easily. At the moment, I didn't put any boundaries, as you see. Okay, so just playing around with constants, I can rewrite it.
squared, right?
Of course. Okay, I'll call this guy x0 and remind you that the cyclotron frequency is okay. That's a definition, and I'm defining this k y. So,
Plus in the beginning?
excuse me?
Plus in the beginning or in the left?
In the left, yes, plus. Okay, so let me tidy it up a bit more. Okay. So, this is definitely the equation of a harmonic oscillator. It's clear. This you have seen in quantum mechanics, or had a question about it, or it appeared in some exam. The shift of the center doesn't change the energy. Essentially, it just moves it by a constant.
What interesting is that the energy isn't dependent on ky. This one.
It's not dependent on ky, but it is dependent on kz. Basically, you have a whole set of solutions. Once you choose kz, you have different energies remaining for the harmonic oscillator motion. Again, makes sense even classically. If I have a total energy, part of it is tied to the free motion in the z direction, and what's remaining is connected to the precession in the xy direction. So, okay, and your remark here is very important. This is the first system that we see that basically has a huge degeneracy for electrons. Why? Because, and basically I have an infinite number of possible KYs.
Oh no.
Oh yes.
No.
Nobel Prizes galore because of that.
Yes, but that just makes it harder to solve. So in that sense, oh no.
No, actually to solve it doesn't make it harder. Why? When you solve the hydrogen atom, once n is larger than 1, you have degeneracies. It didn't make the solution.
Oh no, that part's easy. It's when you have perturbations. That's when the degeneracy gets annoying.
Or useful.
That's what
Annoying for one person is an opportunity for another
it's
person.
annoying because it's a continuous infinity. That's what really bothers me.
Okay, first of all, it is we'll see that in a moment that if we look on the boundary conditions, it removes some of the degeneracy, 1. 2, degeneracy makes life very interesting because then any perturbation has a large effect. If you remember, I'm winging my way around interactions. I say, well, we'll solve the problem for free electrons. In the meantime, only in a box, later on a lattice, but I never take into account interactions. I will actually continue here without interaction. But once I take into account interactions, so we'll see that without interactions, we get very interesting results for the Hall effect. We'll see it's quantized. So that's one Nobel Prize. When you put in interactions, you can get a behavior of the electrons as if they have a third of a charge, a fifth of a charge, all kinds of a plethora of fractional charges, which is known as a fractional quantum Hall. Next Nobel Prize. Then you understand that all these behaviors are topological in nature, and topological matter. First, another Nobel Prize 2 or 3 years ago, that this is a particular case of these topological.
6 years ago by now.
Could be I'm stuck in the past.
We're still in middle school.
You have access to the fountain of knowledge, so you can check it out. And, well, nowadays, I would guess a third or half of the papers coming out in condensed matter in solid state physics are topological this or that.
8 years ago. Or
8 years ago. So all of us are. That's the one with Fowles and...
Yeah, Fowles, Haldane, and Kosterlitz.
Kosterlitz. That's why you shouldn't die young, because one of the effects that they gave is Berezhinsky, Kosterlitz, Fowles. But Berezhinsky had the misfortune of dying before giving out the Nobel Prize, so we missed it. Okay, so how many states? What's the degeneracy here?
Well, for the KC, it's 2. Because you...
Okay, we didn't take your spin into account. Let's forget about
No,
it.
not meaning spin. I mean how, because KC can be in the upwards direction and the downwards.
Right.
and that we do need to account for.
Right.
And then for ky, it's uncountably infinite.
And here we'll try to stop for a moment and see if we can count.
But it's real numbers.
Wait a minute. Well, that should... I'm all the time mumbling something about boundary conditions. One reason that we love so much, let's say, cyclic boundary conditions is that it changes things from uncountable to countable. Right? Once you have, not connected to here, it's a different problem, but just, indeed, physicists love to avoid uncountable things. That's why you use periodic boundary conditions in a lot of the developments of field theories, phonons, everything. Okay, but let me just redefine here, since we love to redefine here things. I want to see immediately the dependence on omega c. Now, square here. Now, this is a Bohr magneton. This appears something actually surprising in some sense. You get here three of the most important constants in physics, determining the energy gap between states, E, H, and C. M, I'm not so sure, is a constant of nature. It's the mass of the particle, in this case, electrons, but till we come up with a good explanation from where it comes, and we have no idea or how even to approach it.
Is it like the angular momentum then?
It has to be connected with angular momentum because you're processing. Okay, so, but this smears it out. So in order to see the naked behavior, what do?
You make a thin.
We make the layer very thin, essentially two-dimensional. Then Kz can be only 0 because anything else will have a huge energy and will be so high up that we don't see it for small ends. And then we can see these degenerate. And here I'll introduce an important concept that will come in the next lectures, band. Why do I call it a band? A lot of energies that have the same value are highly degenerate. Now, so if I'm doing it in 2 dimensions, that's why the quantum Hall effect and the fractional quantum Hall effect are done on 2-dimensional systems, just for general knowledge, and actually we'll go into it hopefully when we are looking on diodes. How do you create in the lab 2-dimensional systems? You should know. And it's not by taking a thin sheet of metal and hammering it till it's very thin.
That's good.
Do you grill it?
The duct tape.
That's high-tech behavior. No, I'm talking about something that you have in all your electronic chips. Silicon, germanium, whatever. It's based on semiconductors. And you take, well, either 2 different semiconductors or 1 type of semiconductors, and you dope. You put in additional atoms that don't belong in different concentrations or different doping between 2 regions, and in the boundary between them, if you do it correctly, electrons have a minimum potential there, so they live on the boundary. We'll see exactly how we get this this behavior, because we'll use it to explain a diode, and if we'll have time, perhaps even to expand it to a transistor. So it's not that we take a very thin sheet of something. We actually create a boundary within a material where electrons love to live, and that's the 2-dimensional system. In order to do it, we have to have very precise growth of materials, so we know exactly how much we dope at each stage of growth, and that the boundary is indeed a boundary and not very fluctuative. And that's basically, till today, the most expensive and hard to replicate part of the semiconductor industry. When the Magnificent 8 left Fairchild Semiconductors. Fairchild Semiconductors is a semiconductor company that Shockley, the guy who took part in the invention of transistors, decided to open a company to do it from his, well, it wasn't his, it was his mother's garage in Palo Alto. And if you're hearing something that you recognize, that is the beginning of the Silicon Valley. He was a great scientist, but a real pain in the backside to work with, and he recruited a lot of good physicists, and they couldn't wait to run away from his company. And what's the point? Was the most important knowledge that they took out of there? 2 of them went on to start Intel. So you see that semiconductor was the cookbook. How to actually grow a clean silicon wafer. That was the most important thing that they took out. They were sued and sued back. I'm not even sure about all the details there, but you can understand at the end of the day, you still have Intel processors in your computers. You don't have Fairchild processors anywhere. Okay, so we got to a point where we understood why 2-dimensional is interesting. But let's try to estimate what is the degeneracy here. Okay, so I have my script. I said that I'll introduce. We know that ky start this one. What did I do here? Well, I put in a quantum number for ky. Now, I estimate the largest KYs that can come into the game. So this is just anything that I would have done for a solution of the type e to the power I ky. But look, I have here x0. I have a center, right? So if the width is Lx, I can't have the center out of the range of the physical open places to put the center of the harmonic oscillator. Therefore, I have a limit on ky. I can't have any ky's that I want, because any ky's that I want will push me outside of the range where I'm allowed to have my center. This is a somewhat imprecise way to put in the boundary condition, but it makes sense. Okay, so how many states or number of states? number in delta ky, number in kz, and that's it.
How is that an integer number?
Look, I didn't say yet that it's an integer number. Well, it depends also on the magnetic field, and for you, I have here a 2. Because there are 2 different ways. I still haven't said it's an integer number. But I do say that I can estimate the number of states.
Look, we couldn't have 3.4 states.
We could. I didn't yet say that. Where do I really hammer it? If I would have closed it into a it's not a torus because well, if I can close it also to a torus where this will be glued to this and this will be. At the moment, I don't even need that. Okay, so I estimated the number of states. For you, if I close it as a torus, I have really a finite number of states. Okay. How is that connected to the magnetism? Okay. Now let's remind ourselves. Something that I told you and probably you have forgotten, and certainly I have forgotten from the previous lecture. We defined Chai. And then I added an additional definition that, as I said, we forgot already about. And now I'm in the frustrating point where I have all the ingredients, but I have to do the calculation. Why? How do I calculate free energy?
With a partition function.
As a partition function. What do I need for a partition function?
The energies.
The energies and estimation of the degeneracies. I have it all. That doesn't mean that life would be easy because it could be challenging calculation, but still I have all the ingredients. So let's go on with the calculation. Don't ask me why I insist on writing 2 pi times h bar. Where did I get it? From the relation for the free energy. So I just wrote it down explicitly. Life is somewhat simpler because I don't have a summation on ky and kz. I can replace it just by the degeneracy and n. So instead of 3 summations, I have just 2. Okay. Since the calculation of the heat capacity, we abandoned hope of simple calculations, but we saw that perhaps we can go forward and do more complicated ones. We'll do this also. Well, actually, it won't be as complicated as the previous one. Well, we have here some function of n plus half. What do we do when we have summations and remember susceptibility is
The derivative.
yeah, but what's the physical condition to what it's trying to express?
The response of the method of the magnetic field.
Yes, with an additional caveat, which makes life much simpler, for example here, at very small fields. So basically, this guy is very small, the B. That's the range where I want to find it. So a summation could be replaced with an integral. So we'll look at one of those wonderful expressions for summations that we have in any math book, or nowadays in Mathematica or whatever. So it's clear that we do here some Taylor expansion. Why it's 1/24, I'll let you to check at home. So, we're back to F. Change the 2 pi times h bar. this guy we haven't yet treated. So what did I do here? Nothing much. Just perform the derivative. Derivatives of ln and exponential are basically easy, and inserted x equals 0. And I'm left with this integral. It's ugly, but I have a result. Okay, what do I do? What's the first thing that I do here? Well, I have still an integral and a summation to perform. Let me emphasize this. Here I stop a moment and tell to myself, look, what did I want actually to find out at the end of the day? Chi, or whatever. What is the most important thing in finding chi? Dependence on b, because I have to. Let me get b out of the game inside the integral. I'll get there a number. I'll either find a way or do numerics or whatever in order to find out the integral, but I'll know the behavior generally without doing the integral. We did it previously. Something that you should always remember. Integrals at the end of the day, if they have no units and don't depend directly on some physical quantity, it's a number. Numbers, unless they come out 0 or infinity, that are problematic. Otherwise, it's a number. I'll deal with it at some point. So, I'll define y. Here I should Remember the difference between mu b and mu of the thermodynamics. Stick it back here. And what do I see?
לא צריך אותי עם בטא?
Well, I can leave the... what up? I prefer to keep the beta inside. No, I prefer to keep the beta outside. So, let's stop a minute to look on what's going on here. Is this term relevant?
No, because the second derivative vanishes.
Second derivative of b kills it. So we are left only with this term. So I'm writing down high, which is equal
So don't you
to...
have another BZ outside of the summation that multiplies everything?
Let me check up here, I'm missing something. Just a moment, I'll get back to your question. I want to finish the first term and then we'll go back. This is what I get from term 2, right? It's not dropping off. It has a b from Mr. b from here, and I'm changing the summation over kz to an integration. Switch the terms. What is left of term 1? Nothing. Switch the terms. Why? Because if I use this bz is incorporated in the integral, and it's not contributing. Just switch 1 and 2. So the only contribution I get from phi is from 2. If you were wondering, I should have remembered that. Why do I bother to put in this correction? Because this is the only correction relevant as b goes to 0. Okay, so if t is small, what did I do here?
Taylor לבטא, לא? Taylor? לבטא.
I didn't, at this point I didn't even need to do this. I just, well, if you want, yes, the first term in Taylor in beta, I just multiplied by e to the power of beta, or whatever. So here I get 1 plus e to the power bh, and I opened it up. Now,
So why isn't it 1 over?
excuse me?
Why isn't it 1 over?
One, no,
After multiplying by the exponent.
sorry, I just open it up as a Taylor expansion.
So it is 1 minus.
Yeah, 1 minus here. Okay. Let's look on the integral. What do we know for small beta? How does this function look?
Like step function.
More or less a step function. So it's a constant and very steep going down. Just kf dk on all the states that are filled times 1. Just kf. We have it from minus infinity to infinity, so it's 2kf. Okay, and that's the end of it. I got the susceptibility. So let's write it down. If I connected all the constants as should be, return to H bar C. Now, K for me is just the density of states at E for me, up to constants. Let's put in the constants. But that's also mu B. And what does this remind us? This is, first of all, diamagnetic. And second of all, it's minus a third the value of the contribution from the spin, from the Zeeman effect, Pauli, which we did in the previous lecture. So, if I want to see how good or bad is my free electron approximation for the behavior of electrons in a metal, I have a very strict way to actually measure it. Measure the contribution of spin compared to the contribution of orbital magnetism. How can I do it different dependence on angle? And I can say something about, do I get the connection as a third? Another interesting thing that one learns from it is that the orbital contribution is weaker for free electrons than the Pauli. So the main contribution that we expect to see in metals is from the spin, and it's paramagnetic. Okay, so basically this is this, but I want to use the quarter of an hour that we have instead of moving into a new subject, which is the influence of the lattice, to look a bit more on the two-dimensional case because of its current importance in physics. So, that's the whole strip, geometry strip, because it's finite in the x direction and finite in the y direction. And it's 2D in this case.
Shouldn't be the length on y. X is the origin.
Oh, sorry. So I'm changing the notation to the ones that we used previously. Okay, so let me ask for a very weak electric field. Do we expect any current? Now I'm considering it classically. So, at first consideration of the problem, the answer is
Yes.
why?
Any small, but even if it's nearly zero, should affect if it's free. If it's free inside.
But is it free? Let's remember, what does a magnetic field? Let's take a finite magnetic field, not a zero magnetic field. Okay, what are the classical solutions?
Form ellipses.
Let's keep it simple.
Just circles, let's say.
Circles. If I look on the net current at some finite region within the sample. Okay, this cyclotron orbit has current to here. The one below it has an opposite current. The net current is
Zero.
0. So if I have an infinite system, I would have 0 current. in the X or Y direction? Well, that we know even from high school physics. We put a particle in a magnetic field, it can move in the Z direction, in the direction of the field. It can't move in the XY direction, the process. So we have no current for infinite. But there is a very subtle difference once we have a boundary. Why? Let's look what happens for a classical particle that had the middle of its cyclotron radius on the boundary. Here. It hits the boundary, and what does it do?
Like start over the process.
It's returned.
It's like the solenoid curve.
It's like a skipping orbit. Continues all the way in one direction. And if I'll do the same game up on the upper boundary, so I can have a current once I put in a net current, because I have a magnetic field. Then you can stop and say something broke symmetry here, right? Why will I have here a current in this direction, here a current in the opposite direction? And what do we have to remind ourselves on a magnetic field?
That the network must be zero.
That a magnetic field breaks time reversal symmetry.
That's where the symmetry breaks boundaries.
On the boundaries.
Wasn't that basically what the Nobel Prize in 2016 really showed? Basically, that those boundary conditions remained for like topological transformations.
That is one of the earliest examples of topology breaking time reversal symmetry or symmetries on the boundary, although basically it's already in the Nobel Prize of 1981. The von Klitzing Nobel Prize from 1981. Okay, let's stop a minute and look on the quantum behavior. Okay, we had basically as the energy, and we decided 2D. So if I'm plotting the energy bands, these guys are the different KYs. I get bands of degenerate states. Now, what happens when I have boundaries? And for us to understand, so if I had a hard wall, basically I would have a limited region of ky's. But in reality, I never have a finite jump. Usually have some potentials that limits the behavior. So something of this type. Okay, so u of x is this behavior. Since more or less the point where it sits x is x0, the center of the cyclotron radius, which is determined by ky. What I have is some states close to the boundary living not necessarily in the band, but going into the gap. Just because you have an additional energy for being close to Lx or 0.
But that is in the reciprocal space, right? And this is in real space. Right?
Yeah, but x minus x0 was in real space.
Right.
Ky is connected to x via this connection. So I have states that if I plot exist mainly close to the boundary. Why can I say it? Because what's the solution of a harmonic oscillator? Falls off exponentially. Right. So if you want to translate this picture to a quantum mechanic, to a wave function, if I'll plot psi square, I'll have basically something like states that behave like this. So if I'm looking on the contribution of ux here, it's 0 because it's still in the flat region. If I'm close to the boundary, it will get some contribution, go up. And these are the states that carry the quantized Hall effect or a quantized current through Hall strips. And it's so well quantized that basically in transport experiments, they behave as if they're a clean 1D system. And you can actually, nowadays, you determine the value of E appearing in the energy out of these measurements. Which, if you stop to think, is crazy. If you want to measure, if I would come to you and tell you, where is it the best to measure the most precisely the charge of an electron? Say, well, I have to somehow get the electron to a place where there's nothing around it and somehow measure its charge in that environment. Turns out that the best place to measure the charge of an electron, the most precise, is in a solid state environment stuck in the middle of the boundary between two semiconductors with 10 to the 23 other electrons zipping around. And nevertheless, that's the most precise way to measure the charge of an electron. which is amazing if you think about it. Okay, so I'll stop here and we'll continue with the effect of a lattice in the next lecture.